Which statement best predicts the sign of delta S for the reaction N2 plus 3H2 goes to form 2NH3? Delta S is greater than 0, delta S is less than 0, delta S equals 0, or the entropy change cannot be predicted. The answer is delta S is less than 0. Because there are 4 gaseous particles on the left-hand side in the reactants, but only 2 on the right-hand side in the products. This means there is a reduction in the total number of particles, meaning less disorder in the system, so the entropy change is likely to be negative. Which situation most strongly suggests kinetic control? Delta G is negative and the reaction is fast. Delta G is positive and the reaction is fast. Delta G is negative and the reaction proceeds extremely slowly, or delta G equals 0. The answer is delta G is negative and the reaction proceeds extremely slowly. This is because a reaction that's under kinetic control is thermodynamically favorable, so it has a negative delta G value. However, the rate of reaction is so slow that the reaction doesn't noticeably proceed, hence kinetic control. A reaction has a Gibbs free energy change that's greater than 0. The corresponding value for E cell must be positive, 0, negative, or greater than 1.0 volts. The answer is negative, because a positive delta G value, so greater than 0, means the reaction isn't thermodynamically favorable. A positive E cell value would mean that the cell reaction is thermodynamically favorable and spontaneous. Since these two are opposites, if delta G is positive, E cell must be negative, so the reaction isn't spontaneous and isn't thermodynamically favorable. Which expression is used to calculate the standard entropy change for a reaction? The sum of standard entropies of products minus the sum of standard entropies of reactants, the sum of standard entropies of products, the enthalpy change of the reaction divided by temperature, or the sum of standard entropies of reactants minus the sum of standard entropies of the products. The answer is the sum of standard entropies of products minus the sum of standard entropies of reactants, with the standard entropy change for the reaction being the difference between the two. A reaction has a standard enthalpy change of less than 0 and a standard entropy change of less than 0. The reaction is thermodynamically favored at high temperatures, low temperatures, all temperatures, or no temperatures. The answer is at low temperatures, because for a reaction to be thermodynamically favorable, the standard Gibbs free energy change, delta G, must be negative. Well, delta G equals delta H minus T delta S. If delta S is negative, then the T delta S must remain smaller than the negative delta H in order for the standard Gibbs free energy to remain negative, meaning only at low temperatures will you get a negative delta G value. Which best describes the purpose of reaction coupling? To slow reactions down, to drive thermodynamically unfavorable processes, to eliminate entropy changes, or to ensure reactions are reversible. The answer is to drive thermodynamically unfavorable processes, because reaction coupling pairs a thermodynamically favorable reaction that releases the energy needed to drive a thermodynamically unfavorable reaction. A chemical process has a standard Gibbs free energy change less than 0 at 298 Kelvin. The process is best described as thermodynamically favored under standard conditions, occurring rapidly, having a large equilibrium constant only at high temperature, or endothermic. The answer is thermodynamically favored under standard conditions, because a negative standard Gibbs free energy means a thermodynamically favorable process. When a system approaches equilibrium, the magnitude of the cell potential increases, remains constant, decreases towards zero, or becomes equal to E standard. The answer is decreases towards zero. Because once a system gets to equilibrium, so Q equals K, then the rate of the forward and reverse processes are equal, meaning no net change overall, meaning the cell potential must be zero. When dissolution is endothermic but still occurs spontaneously, this indicates that standard entropy change is positive and large enough that T delta S is greater than delta H, standard entropy change is negative, standard enthalpy change must actually be negative, or standard change in Gibbs free energy must be positive. The answer is standard entropy change is positive and large enough that T delta S is greater than the enthalpy change. Even though the process absorbs heat, it still occurs because the increase in entropy is large enough to make the overall process thermodynamically favorable. When delta G is close to zero, the equilibrium constant K is very large, very small, close to 1, or equal to temperature. The answer is close to 1, because remember delta G equals minus RT ln K. Well, if K equals 1, then ln 1 equals 0, so delta G is going to equal 0. In all electrochemical cells, oxidation occurs at the cathode, salt bridge, anode, or voltmeter. The answer is anode, because the cathode is where reduction takes place and the anode is where oxidation takes place. Coupled reactions typically share one or more common intermediates, identical equilibrium constants, equal enthalpy changes, or the same activation energy. The answer is one or more common intermediates, which link the two reactions together so the energy from one can drive the other. Breaking the ionic lattice during dissolution generally results in a decrease in entropy, no enthalpy change, a positive enthalpy change, or a negative enthalpy change. The answer is a positive enthalpy change, because breaking the ionic lattice apart requires energy to overcome electrostatic attractions between the oppositely charged ions, so this results in a positive enthalpy change. In a galvanic cell, electrons flow from cathode to anode through the external circuit, from anode to cathode through the solution, from anode to cathode through the salt bridge, or from anode to cathode through the external circuit. The answer is from anode to cathode through the external circuit. The anode being where oxidation takes place, so where the electrons are coming from, and the cathode where reduction takes place, where the electrons are going to. During electrolysis of molten sodium chloride, what is produced at the cathode? Cl2, Na+, NaCl, or Na? The answer is Na, sodium, because the cathode is the electrode where reduction takes place, and the positively charged ions in sodium chloride, Na+, will be the ones that get reduced, and this will happen at the cathode, turning the Na+ ions into Na.